According to the text that I see here, this is going to be a fun exercise. I hope you enjoy working through all of the exercises in this chapter and in this book. But yeah, I think some of them are a little more interesting. Some of them are a little bit more kind of boilerplate. I like to have a mix of different levels of difficulty and involvement in these different exercises. So this one is pretty involved. There's a lot of stuff that you have to do here, and also a lot of thinking and consideration and meditative contemplation about linear algebra. This exercise ties together many concepts that you have learned about in this and previous chapters, including shifting a matrix and the norm of a matrix, correlation, and so on. Okay, so what you want to do is create a 10 by 10 random matrix, so a matrix of random numbers, and compute its Frobenius norm. And then you set up a for loop. So you create the matrix first, and all this stuff you do inside the for loop is on the same original matrix. So you don't want to overwrite that original matrix while you're working through this for loop. Okay, so inside the for loop, shift the matrix by a fraction of the norm. And so that fraction is going to range from 0, which means you're not shifting at all, up to 1, which means you are shifting by the full value of the norm. Now, in practice, in applications, when you are shifting a matrix, the general idea of shifting a matrix is to shift as little as possible. So typical application values of shifting might be 0.01 corresponding to 1%, 2%, maybe a tenth of a percent. Here we're going to go all the way up to 100%. So this is more for purposes of exploration and investigation. Okay, so let's see. So then we want to compute the percent change in norm from the original. So the norm of the shifted matrix versus the norm of the original matrix. That is what you see in this panel over here. So here on the x-axis, this is the amount that we have shifted by. So the proportion of the norm. And then here's the change in the norm. So you can see the more we are shifting the matrix, the larger the norm. And it's in percent here. Okay, and then you want to compute the Frobenius distance between the shifted matrix and the original matrix. And I actually plotted that in this third panel here. So again, the x-axis is the proportion of the norm of the original matrix that we have shifted by. And this is the distance between the original matrix and the shifted matrix. And again, that increases linearly with the amount of shifting. Okay, and then you also want to compute the correlation coefficients between the elements of the two matrices. So correlate the original matrix with the shifted version of the same matrix. And you can see that the more we are shifting that matrix, the smaller the correlation with the original matrix. This is pretty interesting because when we shift a matrix, we are only changing the diagonal elements. We're not changing the off-diagonal elements at all. So therefore, this decrease in correlation really just reflects the fact that we are changing the diagonal elements. And in fact, we're not even really changing them in different ways. We are just adding a constant to the diagonal elements. By the way, it's not trivial that the correlation would decrease while the Frobenius distance would increase. You can actually do other manipulations to a matrix, such as scalar multiplying the matrix, which would change the Frobenius distance without changing the correlation. So the correlation, you could set up different experiments where the correlation stays at 1, but the Frobenius distance is changing. Okay, so that is the explanation of this exercise. And now I will switch to Python. I'll show you how I solved it. Here I have soft coded the size of the matrix in case you want to continue exploring these concepts on your own. This is the proportion of the norm that I am going to shift by. It ranges between 0, which is no shifting, to 1, which is a lot of shifting for an application, in 30 steps. Okay, so here is the matrix, just a random numbers matrix, and I compute the norm of that matrix. You can see that I'm creating that outside of the for loop. So inside the for loop, we're no longer changing that matrix. Here's where I shift the matrix. So it's the norm of the original matrix times the identity matrix, which means nothing is going to happen to the off-diagonal elements. We're only changing the diagonal elements, and then that's scaled by the proportion of shifting. Okay, so this shifts the matrix, and then we compute the norm of that matrix and the percent change of the norm from the original. Okay, and then here I'm correlating the matrix of all the elements of the original matrix with the shifted matrix, and here is the Frobenius distance using this function Euclidean distance, which I created a few exercises ago. All right, so let's run this. And then we get the results. And well, I already explained how to interpret these findings when I introduced the exercise.